Well, thank you very much, and for the opportunity to speak here. It's a great place to be, so I'm really happy to be here. So I'm Karina Caputi. I'm a staff member at the Captain Astronomical Institute, and today I will talk about star formation in galaxies across cosmic times. So this is perfect for this session on galaxy evolution, but as you will see, many of the results I'm going to show are about the high redshift universe, so they connect very much with the talks you've heard on Tuesday. So before going to the results and the slides, I would like to thank all the Midi-European GTO team and the High Redshift Galaxy Group, because most of the work I will show today has been done in collaboration with all these people. And in this list, I want to emphasize and highlight the names of my people in my research group, postdoc Edoardo Ianni, and PhD student Pierluigi Rinaldi. They are doing amazing work as associates in this team, and you will see their results in the next slide. So the big question in this talk is, how do galaxies form their stars? In the present day, in the local universe, we know that in general, new star formation happens at moderate rates. And this is how spiral galaxies form stars in their circular evolution. So welcome back. Sorry. Yeah. All right. So quantitatively, what we mean by this circular evolution is that the birth rate parameter is lower than 1. The birth rate parameter is the ratio between the ongoing star formation rate and the average past star formation rate. There are other types of galaxies where the ongoing star formation rate is enhanced, very much enhanced with respect to the average past, and we call them starbursts. And these galaxies are very rare in the local universe. So the big question is, when we study galaxy evolution, is, has it always been that way? Have these starbursts always been so rare? So the search for starburst galaxies has been going on for many years now. And over the past decade, the sub-millimeter community really led this search. Actually, in the sub-millimeter community, the word starburst has been wrongly used for many, many years because they were just meaning galaxies with high star formation rate. The majority of galaxies forming stars follow what we call the main sequence, which was presented by Stacy before. Here, what you see is the star formation rate versus stellar mass plane. And you see that the vast majority of galaxies lie on a sequence with significant scatter, of course. Only a small amount of galaxies are seen to have an enhancement of their star formation activity for their stellar mass. And this is what we call starbursts. In the Herschel times, people looked for these starbursts between redshift 1 and 5 and concluded that starbursts, even at high redshift, were still very, very rare. So the conclusion was starbursts are really not important. But I will add that that conclusion was dependent on the fact that these galaxy surveys only could prove very high stellar masses, above 10 to the 10 solar masses. Some years later, we did a study of star formation in much lower mass galaxies based on Spitzer data. So we looked for H-alpha emitters between redshift 4 and 5 in the cosmos field, and we found, again, we put all these galaxies on the star formation rate versus stellar mass plane, and we found that there were clearly two sequences of star formation. The main sequence that everyone recognizes, and a good amount of galaxies with an elevated amount of star formation rate. This is much more clearly seen in a histogram of the specific star formation rate, which is the ratio between the star formation rate and the locked stellar mass in the galaxy. And there you see two peaks, the main sequence peak and another peak at higher specific star formation rates corresponding to starbursts. So empirically from here, we can define the starbursts as galaxies having this value, this cut in specific star formation rate, which may seem a bit arbitrary to you, but if you invert the specific star formation rate, what you have is the stellar mass doubling time, which has a very specific meaning. And the stellar mass doubling time in these starbursts are actually consistent with the timescales for starbursts that we know in the local universe, which is a few times 10 to the 7 years. So this was only for H-alpha emitters, but then we generalized this result, studying all galaxies in these fields, but also with other data between redshift 2.8 and 6.5. So the sample was much broader, and all galaxies forming stars selected from the UV, and we found exactly the same result. And here what you can see is that at this redshift, stars make in number 35% of all star-forming galaxies. And actually, in the star formation rate budget, they make for 80% of all the stars being formed at this redshift. So for some time, all this work came out from my research group. And for some time, there was not much consensus in the literature about the existence of this starburst galaxy. But I'm very glad to report that now, in the JWST era, everyone is seeing starbursts at high redshift. So now we are claiming, we were right. So JWST results. So we are looking for the starburst galaxies at different redshifts. This is still from my research group. I will show some other results a bit next. This in particular is the study of starbursts among Lyman alpha emitters between redshift 3 and 7. You have upper panels for the Lyman alpha emitters and the lower panels for star-forming galaxies which do not display Lyman alpha emission. We call them Lyman break galaxies. On the left, you see, again, the star formation rate versus stellar mass plane. And on the right, you are seeing the specific star formation rate. And there, again, you see clearly two sequences, the starburst and the main sequence. And this is telling you, already with this work, that the fact that the galaxy is a starburst or not is not necessarily linked to the presence of an emission line. Emission line doesn't tell you that the galaxy is a starburst immediately. It just tells you about star formation. But even more, if you look at the low panels, the Lyman break galaxies don't have prominent emission lines, but still you see some starbursts, which are derived from the UV luminosity. So again, the connection is not one-to-one. I will come back to this point just next. Something even more interesting is that we could look for starbursts among H-alpha emitters at the epoch of reionization. To search for H-alpha emitters at this high redshift, I'm talking about redshift 7, you necessarily have to go to MIRI images. So this is one of the great powers of MIRI. MIRI is the only instrument that can catch the H-alpha line at the epoch of reionization. So we exploited ultra-deep MIRI images to search for H-alpha emitters at redshift 7 to 8. We found quite some nice candidates. And what we could derive is that these H-alpha emitters, not surprisingly, have very high photon production efficiency, which makes them very good candidates to have had an important role in the process of reionization. So these galaxies likely were very important for reionization. Now, at the bottom here, what you see is this photon production efficiency as a function of the specific star formation rate. And what you see is that there is sort of a broad correlation, and the sources with the highest photon production efficiencies are really starburst galaxies, which are in this blue zone. So the most prominent H-alpha emitters were starburst galaxies. But we are going to see that this is not true in the reverse sense. So transitively, you can say that starbursts likely had a crucial role in reionization because the most prominent emitters were also starbursts. These are other results from the literature. It's not just us, as I said, looking at this and seeing starbursts. Actually, many people are studying very high redshift galaxies, and by modeling the star formation histories of these galaxies, they modeled the spectral energy distributions. They found and they infer that many of them must be passing by a starburst episode. So starbursts were really common at high redshift. Now, all these works that are coming out over the past year really leave us with several open important questions. Were the sources of reionization starburst galaxies? Well, we've seen that likely yes. What is the relation between prominent line emitters and starbursts? And are the line emitters representative of all star-forming galaxies at high redshift? And I ask this is very important because many works are based on spectroscopy, so they preferentially select Lyman alpha emitters. Sorry, not Lyman alpha emitters, rather line emitters in general. So I will try to focus on the answer of these two questions in the next slide. So in another piece of work, we studied the relation, this time between H-beta plus O3 emitters and starburst phenomenon at the epoch of reionization. So what we have here at the top is the equivalent width of this line complex versus the specific star formation rate. And again, we found that the most prominent line emitters correspond to starburst galaxies. So this is really like that. The most prominent line emitters are starbursts. However, something you have to note in this plot are these upper limits, these gray points. This corresponds to galaxies with no significant line emission, but still, from the UV luminosity, you can deduce that these are starburst galaxies. So this is telling us two things. On the one hand, that there are non-emitters that are starbursts. So the relation is not one-to-one. And the second point is that if you really want to take into account all the star formation going on in the universe, you have to also look at galaxies which don't emit, don't have a line emission. How do you explain these starbursts which are not line emitters? Well, you have to go to galaxy models. Look at this plot at the bottom. And don't concentrate on the data points, just focus on the green lines. The solid lines are showing you the case of the evolution of the equivalent width of the line as time passes for a continuous star formation history. This is from the Starburst 99 models. If you look at the dashed line, this is the evolution of the line equivalent width for starburst galaxies. So if you have a continuous star formation history, star formation always goes with high emission lines. But if you have a starburst, the emission lines are very prominent only at the very early stages of the starburst phenomenon. And the emission lines will decay very, very quickly. So, and this means that the time scales for star formation traced by the UV luminosity and the line emission are different. With the UV luminosity, you prove time scales up to 10 to the 8 years, while the emission lines in the starburst will only trace the star formation going on in the first million years or so. So the relation is not one-to-one. So, and this takes me to my conclusion. Well, first of all, JWST results are indicating that the starburst mode could have been the dominant mode of star formation activity in the early universe. And starbursts are all young and low stellar mass galaxies. And they are prominent line emitters, but only at the beginning of the starburst phase. So we think, and this is, of course, this needs to be proved further, is that the starburst phenomenon is really linked to the process of reionization, but when they contributed the most was in this period of intense line emission. And the final point is that galaxies without prominent emission lines can also be starbursts. So if you really want to consider the whole cosmic star formation rate density, you need to take into account the line emitters and the non-emitters. Thank you.